Welcome back everyone to chapter 12 and the video in which we will add the final bits to our discussion of merge join. Okay, so some observations I would like to add to our discussion of merge join. There are some corner cases and some challenges that merge join is facing and also some opportunities, and I would like to add these to the pile of observation that we've already made regarding merge join, and then we will call it a day regarding merge join and switch over to hash join in an upcoming video. All right, so hash join is an interesting algorithm, and it's actually the go-to equi-join algorithm that a modern RDMS would choose. We will see that PostgreSQL also favors hash join over other join methods if this is possible at all. But if memory is tight, then merge join appears to be a quite attractive alternative. Well, hash join, as you can imagine, will of course construct hash tables while it does its job, and we will of course look at the details of how these hash tables are being constructed and then used. But, well, hash tables need memory, and if working memory is really tight, then merge join might be an interesting option to pursue. Because if you look at the behavior of merge join, if the inputs are already sorted according to whatever circumstances because of index scans or some interesting orders that have been generated in the subplans, well, then only the actual merging that is being performed by merge join only needs 3 buffer pages. So we would be content with 3 buffer pages. 2 of the pages would be used to hold the current rows of the left and right input tables. And in one of these pages, we would construct our joined output. Of course, whenever the output page is full, we would just flush it and then, make room for the generation of new output rows. Okay. There's one requirement that has to be satisfied that indeed leads to this very, very attractive low memory requirement, and it's related to the rescanning of the right input. If there is indeed the need for rescanning of the right input, resetting the right read pointer in the right input table and reset it to some marked position, maybe far away, far back, then, well, of course, we would need memory to temporarily store that portion of the right input and to make a rescanning possible there. So we would only see these very low memory requirements of merge join if indeed such rescanning is not needed. Okay, this is the case, for example, if the left join column, the CL column of our left input, is a unique column, which is not too uncommon. Maybe we are talking about foreign key joins, then the CL column here might indeed be a primary key of the left table, and then it would be unique. Unique CL values means there are no repeating groups in the left-hand input table, and it's exactly these repeating groups that led to the need for rescanning in the right-hand side input. So if the left input is indeed unique, no rescanning, then low memory requirements. We don't need working space in the database buffer to hold pages of the right-hand side table ready for rescanning. Okay. Indeed, as you will see in the plans that PostgreSQL generates, that the system is aware of this very favorable property, and it will indicate this by adding this annotation to its plan. Inner unique is true. Well, inner refers to the left-hand side input here. I don't think that inner is the best term that the PostgreSQL folks could have used here, but well, it's how it is. Inner unique true indicates that there are no repeating groups in the left-hand side table and that the memory requirements of merge join might be low. Indeed, we can also simplify the merge join algorithm itself. If you recall the pseudocode for the merge join algorithm, let me check. There it is. If you recall, then there was quite a few bits here, quite a few bits that were concerned with the management of the rescanning. And well, if the left input is unique and there just is no rescanning, well, we should be able to simplify the pseudocode for the merge join algorithm. And I would like to invite you to think about the simplified code, to think about the pseudocode that you would write for the merge join unique variant of merge join, where we can assume that there are repeating groups in the left-hand side input. Why don't you spend a few minutes and a few pencil strokes on on this pseudocode? I think it could be insightful. All right. Right, so let's switch over to the terminal quickly and see whether PostgreSQL can make use of that and what are the consequences for memory usage and so on. All right, here we go. What I've brought with me here are two new playground tables. That have a value distribution in their join columns that will fit the experiment that we are trying to perform. Indeed, we are looking for unique values in these join columns so that the rescanning can be avoided. And I'm also preparing a value distribution here that we will use later in a subsequent experiment. And that leads to some interesting behaviors about the scanning behavior of merge join and how the read pointers are forwarded in the left and right hand side inputs. So I've already created these two tables. They are the tables left and right, and they both carry 10 million rows. These are the two column schemata of both tables, and this is the value distribution in these tables, the instances of the left and the right table. Okay, you can see that there is, of course, both tables will carry 1 million rows. But in the A column, which will be our join column, the value distribution is a bit peculiar. So maybe it's worth to quickly switch over to a piece of paper and draw what we are generating here. Okay, so we are generating two tables. It's the left table and the right table. Both have a schema of A and B. All right, so that would be the left table. Of course, the left table will be filled with values. Let me extend this with values 1, 2, 3, and so on, and up to 1 million. So let me sketch the tail of the A column here. It would carry values like this. So, and the last value will be 1 million. Check, check. Okay, so that would be, let me scroll this a bit up here. So that would be the distribution of values in the left table. In the right table, it would look a bit different. So let me indeed sketch the table like this. So it would also be an AB table. All right, like this, and it would start actually with the value 999,000. Okay, and then would of course reach 1 million here. Okay, and then of course extend beyond that. We need 1 million rows altogether. So you can see that there is some overlap between the contents of the join columns in the left and right tables. It's exactly this area. And that area will indeed contain 1,000 rows. So when we perform the join between the left and right tables here, can I fit this in? Yeah, I can fit this. Okay, so if we perform the join between the left and right tables here, then there will be a join result that will hold 1,000 rows. Okay, so no join results are being produced in this upper part of the left table, and no join results will be produced if we scan beyond this 1 million value here. All of these values are larger than any value in the A table, so no join partners can be found there. So This is the value distribution in the left and right tables. Okay. So much for that. Here we are again. So I've already populated these tables. Take some time. Well, I can show you the tail, beginning of the tail of the left table. As you can see, this would be the beginning of the tail. All right, so we are in the 999,000 value range here. And if I show you the first few rows in A order of the right table, then you will see that there is rows that carry the same A value. These are part of the overlap, and these will lead to joint partners. Only the 1000 rows in this range will lead to joint partners. I've already created indices on the left and right tables. Both indices are defined on the A columns. The A columns will be our join criterion. So wow, so perfectly suited B plus trees that should be exploitable by merge join. They will deliver rows in the interesting A order, which is exactly the order that we will need, the sorting order that we will need to employ merge join. And I've already analyzed these tables. You see that I've used the unique modifier here while I created the index. This prompts the system to indeed check that the contents of the A column is unique. There are no duplicates to be found there. So the system is informed of the fact that we are looking at unique A columns in both tables. Okay, so much for the setup. Okay, so and now, well, let's have a look. Let's have a look at an equijoin between the left and right tables, of course, on the A columns as we proposed. Okay, let's see. There we go, already done. So indeed, this is a merge join. A merge join has been used, and indeed the inner unique flag has been set to true here. So the system is indeed aware of the fact that the left-hand side input is unique. There will be no rescanning. Memory requirements will be low. Okay, right. And well, this is the input to the merge join. Of course, both sides would use the index scan on the A columns to produce the left and right input rows in A order already. Okay, what's interesting here is that on the left-hand side, indeed, all 1 million rows have been scanned. Well, we started at the very beginning of the A order of the left-hand side tree, only to find rows with A values that are way too small, right? Only in the tail of that index scan we will find possible hits that can contribute to the join result. It's different actually on the right-hand side of things. You see that the system or the merge join indeed only scans 1000 rows. These are indeed the 1000 rows in the overlap that will produce the join results. The system does not scan any further. It is aware of the fact that it's scanning a sorted structure here as the sequence set of this right underscore AB plus tree. This will produce the rows of the right-hand side table in A order. Once we have exceeded the maximum value, the maximum A value on the left-hand side, we will only see larger A values here on the right-hand side. It just makes no sense to continue the index scan at this particular point, and we might as well stop scanning the sequence set. And this is exactly what happens here. The system makes use of the fact that both structures here are ordered. We have already seen the maximum A value on the left-hand side. Makes no sense to scan beyond that maximum A value on the left-hand side in the right-hand side. Okay, so that's all very, very favorable behavior here. So we are content with that. So now let's switch off merge join. And since this is an equijoin situation, well, the system will then consider hash join for execution. And as I told you already on the slides, this might not be the best idea because, well, hash join is not using is not using the availability of order and indexes. And as we then will see in the second step, hash join has some rather hungry memory requirements. And this is can lead to problems. Okay, so let's first switch merge join off temporarily and then look at the current working memory that is available. This is the 4 megabyte default. Okay, right. So let's see. This is the same query again. It will be evaluated and planned without merge join. So probably hash join will get its time in the light. Okay, so this took a bit longer. Right, so that's a hash join. Also, the hash join is informed about the uniqueness, and that can also be helpful for a hash join. All right. So you see, of course, the left and right tables will deliver their input into this hash join. But as you can see, no mention of the indices. We are performing sequential scans on the left and right hand side table. Indeed, hash join is one of the join algorithms that cannot exploit the presence of indices. Okay, so it's not being exploited here. You will also see that the scans on the left hand and right hand side tables indeed visit all the 1 million rows here. Okay, so no exploitation of order or premature ending of scanning or reading the table. So nothing like this is happening here. And well, there has been some memory usage. All right, so 2 megabytes, 2.7 megabytes, and this batches number, of course we will come back when we talk about the details of hash join here, but this batches number already suggests that hash join had a hard time to fit its operation into the available working memory. So let's make the scenario for hash join even more difficult and set the working memory to the absolute minimum of 64 kilobytes. So of course I do not recommend that you configure your database system like this. This is just to simulate tight working memory, maybe because there are a number of concurrent users that are working with your database system, and well, there's only so much working memory that you can be allocated at a particular time. Okay, so let's do that. Very minimal working memory. Remember, merge join is still switched off, so let's revisit this query and evaluate it again. Again, hash join will be used, but well, there's probably some real effort to be performed by hash join here. Okay, so we are waiting already. All right, so this took like almost 16 seconds, which is 10 seconds longer than we've waited before. All right, so the whole setup of the plan, the shape of the plan has not changed, but as you can see, oh yeah. So of course we were not allowed to use more than 64 kilobytes of working memory, so we were content with 41 kilobytes here. But this led to a very high number of batches. And as you will learn when we look at hash join, this points to a high number of iteration, repeated reading and writing of buffers in the operation of the hash join, which really has some severe performance impacts here. Okay, so under low memory requirements, hash join really struggles, as we can also see in the overall execution time here. Now let's switch back on the merge join, and let's remind ourselves that the working memory is still tight. It's 64 kilobytes. 64 kilobytes, but now the merge join is an option again. All right, so one final time, let's re-evaluate this particular query here. We will hope that merge join is going to be used. The inner unique or the left hand side unique flag will be true. No need for rescanning. We are content with really very little memory here during the execution of merge join, and hope that we can see the impact here. Let's see. Oh yeah, that went quicker, less than a second. Perfect. And well, yeah, indeed, the system can do with really little memory in a merge join that needs no rescanning, because the left-hand side or the inner, as annotated here, is unique. Perfect. Okay, back to a sensible amount of working memory. All right, so this was one detail I would like to show you, and then here comes the final detail that we would like to add to our discussion of merge join. And this is about, well, two challenges for merge join in a sense, right? So think about large groups of repeating values in the right-hand side input. Well, we have talked about repeating values in the left-hand side input and how these may lead to rescanning effort, right? But what about large groups of repeating values in the right-hand side input? Well, this may lead to situations in which the positions of the marker and the actual reading position that we have in the right input diverge very significantly, right? So we are advancing through the large repeating group of values in our right-hand side input table, and well, there will be quite the distance. The size of the repeating group will be a measure for the distance between the marker and our actual reading position in the right-hand side input. And recall that we need to keep all the rows of the right-hand side to be ready for a rescan, that a resetting of the right-hand side input pointer to the marker. Right, so such large groups of repeating values can lead to very high memory requirements regarding all the rows that need to be buffered for rescanning in the right-hand side input. So that can indeed be a challenge for merge join. And well, again, I would like to invite you to think about the worst case here, which should be really rather obvious. Okay, so, well, of course, the worst case would be very unusual, and it's probably not something that you have to worry about in a real workload, but well, you might encounter that case, and the system has to react to that. The requirements regarding memory can be really significant. So that would be one challenge, right? Another challenge, the final challenge I would like to address here is this. It's large gaps between the join columns in the left-hand side and the right-hand side inputs. So left CL and right CR and the gaps of values between these. Okay, so let's again consider the left-hand side here, the left-hand side of this schematic. So I'm looking at this particular left-hand side here. We would like to perform a merge join between the left and right tables. CL and CR, as always, are our join columns. All right, so merge join is indeed on the lookout for join pairs in which the CL value and the CR value are indeed the same. This would lead to the generation of our first joined row, the join output. Well, in the value distribution that you see here in this left table, you see that, well, of course, we would start our scan in the left-hand side, on the left-hand side at this particular position here, and we would find that there is indeed no join match to be had. 1 and 1000, there's quite a considerable gap between these two values. So we would advance the left-hand side pointer, read pointer, to try to find CL values that are larger and would finally approach this really large CR value here. Okay, and we would perform the scanning here, and that scanning would go on and go on and go on, and it would take its time. It would take its time until we finally reach a value region inside the left-hand side table, inside the CL column, that can contribute actual join partners. All right, so we really need to invest some effort to scan the gap here. Okay, right. This is how it's indeed implemented inside PostgreSQL in most implementations of merge join. There is, however, the idea of using available indices, B plus tree ordered indices, to try to jump the gap. Okay, so the initial situation would be the same. Of course, we would like to join the left and right tables, and the value distribution is the same awkward distribution that we have seen on the left hand side of our picture. The scan would start with CL and CR values that are considerably far apart. There's a gap there. Okay, in this right hand side scenario, however, we've got a B plus tree on the CL column of the left hand side table. So it would be the left underscore CL B plus tree. All right, so since we know that we are actually on the lookout for CL values that can match this large CR value, why not use the B plus tree? Why not use the B plus tree? Enter it at the root at the B plus tree with this particular index condition and start a search for CL values that can indeed match this large CR key value. All right, so we would enter the B plus tree, we would perform our search, and the search would lead us to this particular row ID, which when we follow would immediately lead us to the first row in the left hand side table that would be a match for the large CR value here. Indeed, we have jumped the gap. We have performed an immediate jump without scanning to the correct or to the promising area of values, CL values in the left hand side column, all with the help of the B plus tree. Of course, such jumping the gap might occur often during such a scan. Such gaps might occur many times in the value distribution of these left and right hand side columns, and we could maybe use this B plus tree jumping the gap technique many times during the scan, the merge join scan in the left and right hand side tables. All right, and this is indeed a promising technique. It's not implemented inside PostgreSQL, however, which is a pity, as I will show you now as the final bit in this merge join discussion, because it could really lead to some improvement in the performance of merge join. So let's switch over to the terminal again. All right, so here I would like to demonstrate the jumping the gap technique. Demonstrate this technique on the level of SQL. So I will write a SQL query here, or use a SQL query that simulate this the behavior of the merge join that produces a lockstep movement of the left and right file pointers, but also uses a B plus tree index to jump the gaps. So indeed, we are assuming that there are B plus tree indices on the left A and right A columns of our input tables. If you remember, when we created the left and right tables like 10 minutes ago, we created such indices. So that's perfect. I also will show you a simplified variant of this jumping the gap technique that indeed will not perform any rescanning. It will assume that the left and also the right hand side tables in this particular simple example are indeed unique. Only for such unique columns, the implementation that I will show you now, or at least the sketch here, will perform correctly. All right. So first, let's rerun the original merge join built into PostgreSQL. Of course, it's no jumping the gap technique. This will really be tedious scanning of the first 999,000 rows of the left-hand side table, starting from the first row until it reaches the value area of CL values at the very tail of the left-hand side table that can then match the rows on the right-hand side. Okay, so let's recall. Okay, so 850 milliseconds here. That's what the normal scan-based technique can deliver. And here is the jumping the gap formulation of the query. It's a monster query. All right. Okay, and it also uses the with recursive construct that you might not be used to. You might have come across this construct when you are also subscribed to the advanced SQL course But well, let me only sketch this particular query. Well, this will compute a two-column relation with recursive, a two-column relation in which the left-hand side, or the column L here, will represent the read position in the left-hand side table. In the R column, I will maintain the right-hand side read pointer in the right-hand side table. Because I cannot maintain pointers here, I will indeed maintain the whole tuples in the left-hand side and right-hand side tables that have already been reached during the merge join lockstep scanning. So that's why I start with all of my scanning in the left and right tables here by looking at the minimum LA and RA values. So I will position my scan pointers at the very beginning of the left and right input tables. And well, the left and the right row that I find there at the very beginning of these tables, those will be placed into this merge table. This will be the very first step, the base case of our recursive query. In the recursive query itself, you can see that in this recursive query itself refers to itself. This is the recursive part. It will then look at the current scan position that we have reached and compare the key values, the join key values on the left-hand side and right-hand side tables. In case the left-hand side is less than the right-hand side, well, then we would try to advance the read pointer in the left-hand side. And that's what we are doing here. We are reading in the left-hand side, and we read as far as we reach the A value on the right-hand side. That would be our criterion, how far we have to move in the left-hand side. Okay, and this predicate is perfectly well supported by the A index on the left-hand side table, and indeed that index will be used here. All right, so this is indeed the jumping the gap technique. To find the next row L1 that can actually match the current A value on the right-hand side, we will use the B+ tree to perform this particular query, and we will indeed jump the gap. Well, we will not perform a full sequential scan, sequence set scan in this B+ tree because of this limit 1 here. So we will indeed only deliver the first row that the index can deliver here. And all of the rest actually mirrors this basic idea of this first clause here. Let's not dive too deep into this. Let's only appreciate that jumping the gaps in this fashion using B+ trees can indeed make a performance difference. So let's recall 850 milliseconds. That's what the scan-based built-in merge join of PostgreSQL can deliver. This super complicated query that builds on the jumping the gap technique can perform the same operation in 160 milliseconds, right? So that's an improvement of 5 times. And well, imagine the possibilities if all of this would actually be implemented and expressed using the actual implementation data structures of PostgreSQL itself, implemented in C and so on, without the formulation of such a complicated SQL query. The opportunity there is huge, I would say. Well, there are some future updates of PostgreSQL to come. Maybe at some day there will be jumping the gap with B+ trees. Right. All right. I think that should conclude our discussion of merge join at this particular point. I hope you found that insightful, and I hope you're still keen to learn more about join algorithms, because there will be one more section of videos in this chapter 12 that will talk about hash join. All right, so hope to see you there. Take care. Bye-bye.